In this video, we are going to do some more stoichiometry practice, writing a chemical equation, practicing the conversions, and that sort of thing. So first off, it says solutions of sodium carbonate and nitric acid are combined, and we need to predict the products and also balance the reaction, and they give us a little hint. So first, let's do the formulas for sodium carbonate. So sodium is Na, and just as a reminder, it is right here on the periodic table. So it's an alkali metal, it's in that first column. It's always going to have a charge of 1 plus. Carbonate is a polyatomic ion, CO3 with a charge of 2 minus, so that is something that you need to memorize. So if we were going to make a neutral compound out of sodium and carbonate, we would need 2 sodium ions to buddy up with the carbonate. And it does say that there's solution, so that means it's dissolved in water, so I'll give it a physical state of aqueous. And then nitric acid, so the acid nomenclature, ic means that the polyatomic ion that it came from ended in ate, so nitric means that it's the polyatomic ion nitrate, and nitrate is NO3 with a minus charge, so again, that's something you need to memorize. The polyatomic ions, generally, you have to memorize them. And it says nitric acid, so there's going to be hydrogens here. Now, since the nitrate polyatomic ion has only 1 negative charge, then just 1 hydrogen will be required. So HNO3 is the formula for nitric acid. And I will also call it aqueous since it's a solution. And then we have to predict the product. So general advice is you can go ahead and think like double replacement. So I'm going to have the sodiums and the hydrogen switch places. So, and I'll write it up top just so we work out the formulas. So that means we're going to have sodium and nitrate trying to form a neutral compound. And then we're also going to have the hydrogens, which hydrogen is 1 plus, and the carbonates trying to form a neutral compound. Now, if you take sodium and nitrate, you only need 1 of each to make a neutral compound. So NaNO3. And then if you were going to take hydrogen and carbonate, since carbonate has a 2 minus charge, that means the formula for the compound we create must be H2CO3. And then by our solubility rules, so to review the solubility rules, generally one of the rules says that any compounds with nitrate in it are soluble as in they dissolve in water, so the physical state is aqueous. Another rule is anytime you have an ammonium compound, they're also aqueous. And another rule is anything with group 1 metals. So anything in that first column, so like hydrogen, lithium, sodium, etc., those are all going to be soluble, so we call them aqueous. So we can safely say that both of these are aqueous. Now, let's take a look at our hint. It said carbonic acid decomposes into carbon dioxide and water. This thing right here, that is carbonic acid. So CO3, the name of that is carbonate. And then if you turn it into an acid, which is essentially what we've done by putting those H's in front, the ATE turns into ic. So the name for this would be carbonic acid. So our hint is telling us that this compound right here is going to actually decompose into carbon dioxide and water. So what that means is our final chemical reaction is more like Na2CO3 aqueous plus HNO3 aqueous yields NaNO3 aqueous. And then instead of writing H2CO3, the carbonic acid, we're going to write carbon dioxide gas plus liquid water. So that's the actual chemical reaction. That's like the final answer for just the chemical reaction. And then just a quick check to see if it's balanced. So let me switch up colors. I see there's 1 nitrate right here, 1 nitrate ion, and there's 1 nitrate ion over there. I see that there's, let's actually do with the sodiums. So there's 2 sodiums right there, but there's only 1 right here. So that's going to be a problem. The carbonate, or let's just focus on carbon. There's 1 carbon there and 1 carbon there, so that's okay. And the oxygens, there's 3 there. and we have 3 from over here. And then with the hydrogens, there's 1 hydrogen here, but then there's 2 in the water. So essentially what's not balanced is the sodium and the hydrogen. We could also think through this. I'm going to have to erase this work. We could also do it like this, where we have the sodium, carbon, oxygen, hydrogen, and nitrogen. So I'm doing it element by element. So 2 sodiums on the left, 1 on the right, 1 carbon on the left, 1 on the right. Oxygens, I've got 6 total on the left and 6 on the right. Hydrogen, I have 1 on the left, but 2 on the right, and nitrogen, 1 on the left, 1 on the right. So again, it's the sodium and the hydrogen that's not balanced. So one thing that we could do is we could put a 2 right here in front of the nitric acid that's on the left side. And then of course, anytime you do make a change like that using the strategy, make sure you update your count. So the hydrogen, instead of 1 on the left, now there's 2 of them. The nitrogen, there's 2, and the oxygen, there's 9. And then if we put a 2 in front of the sodium nitrate that's on the product side, then now there's 2 sodiums on the right side, and there's 2 nitrogens here, and there's a total of 9 oxygens. And now it's balanced. And the reason why balancing is important, because later in this video, we're going to need the mole to mole ratio in order to convert from moles of one substance to moles of another. Having the balanced chemical equation is crucial anytime you're doing stoichiometry. So anyway, that's our equation. Got 1, 2, and then 2, 1, and 1. So let's do the next part. It says, how many moles of sodium carbonate are required to produce 50 grams of water? So our strategy is we're going to start off with the 50 grams of water, and we're going to convert that to moles of water. And then we're going to convert that to moles of the sodium carbonate, which is Na2CO3. And since they asked for moles, we will just stop there. We don't need to convert moles to grams because they didn't ask for grams, they asked for moles. So here's how our setup is going to start. We have the 50 grams of H2O, and we're going to need 2 conversions. So I drew 2 arrows right here, so that kind of a reminder that we have 2 conversions necessary. So I'm going to draw my 2 big parentheses, and we'll set this up. Now, for the first one, to go from 50 grams of water to moles of water, we need to use the molar mass. So anytime we're going from grams to moles or moles to grams, we use the molar mass. Now, I want the grams of water to cancel, so I'm going to put that on the bottom. And I want to convert it to moles of water, so the moles goes on the top. Now, in terms of the number that gets put in there, we want the molar mass of water. So just as a reminder on how we calculate molar mass, the formula for water is H2O, so we need the molar mass for hydrogen, and since there's 2 of them, we'll do 1.01 times 2, and then we get the molar mass for oxygen, and since there's 1 oxygen, just that, 16, so it's about 18 grams per mole. We got 16 plus 2, so it's about 18 grams per mole. So I'll just use that. And it's 18 grams per 1 mole. So molar masses are always some number of grams per 1 mole. So I'll have 18 on the bottom and 1 on the top. Now the second molar ratio, the second conversion is the molar ratio to go from moles of water to moles of sodium carbonate. So we look at the balanced chemical reaction to figure out what numbers we put in. But in terms of our units, we want moles of water to cancel. So I'm going to write that into the bottom. And on the top, I'll write moles of sodium carbonate. Now, in terms of what numbers, we look at our balanced chemical equation. We had, for every 1 mole of sodium carbonate that reacts, we make 1 mole of water. So it's just a 1-to-1 ratio. So mathematically, it's trivial because, on your calculator, some number multiplied by 1 times 1 is just that same number. But it's really important anytime you have to show your work to show that step, because it's really showing how we convert our units. So I just showed the units canceling. Grams of water cancels, and then moles of water cancels when we use that mole to mole ratio. So then in your calculator, you would do 50 grams divided by 18. And you should get 2.78, and the units are moles of sodium carbonate, Na2CO3. And then just a quick check on the sig figs. So they did say that we had 50 grams of water, so that 50.0, that value has 3 sig figs. So using 3 sig figs is appropriate here. Now, I did kind of round a little bit with my molar mass. I just wrote 18, but if I kept more sig figs, I'd have 18.02. You should never limit your sig figs based on your molar mass, but you also shouldn't be lazy like I was and round off your molar mass arbitrarily. But anyway, 2.78, that's what we should get. So next one, it says, if 7.50 grams of sodium carbonate react, how many moles of carbon dioxide are produced? So again, our strategy, similar to last time, we're going to have 7.50 grams of the sodium carbonate that we're going to convert into moles of sodium carbonate, and then we're going to convert it into moles of CO2. So let's begin setting this up. We have 7.50 grams of sodium carbonate, and we're going to need 2 conversions. So the first one, to go from grams of sodium carbonate to moles of sodium carbonate, we need the molar mass of sodium carbonate. So let's go over to our periodic table. I'll erase what I had before for water. The formula for sodium carbonate is Na2CO3. So sodium is over here, 22.99. And that's going to be times 2 since there are 2 sodium atoms in the formula. And then we'll have 1 carbon. And then we'll have 3 of the oxygen. And when you do that on your calculator, you should get about 105.99 grams per mole. The units of molar mass are always grams per mole. So let's go ahead and use that value over here. Now, since I have the units of grams at the moment, and I want grams to cancel, I'm going to put the 105.99 grams on the bottom and 1 mole on the top. Ran out of space a little bit, but it's okay. Next, converting from moles of sodium carbonate to moles of CO2, we need to use the mole-to-mole ratio. So again, we're going to look at the balanced chemical equation, and it's a 1-to-1 molar ratio again, because for every 1 mole of the sodium carbonate that reacted, we produce 1 mole of CO2. But it's an important step to show. So 1 mole of Na2CO3, that goes in the denominator for every 1 mole of CO2. So then just showing the units canceling. Grams of sodium carbonate cancels when we use the molar mass, and moles of sodium carbonate cancels when we use the mole-to-mole ratio. And here on your calculator, you should get 0.0708, and the units are moles of CO2. And just checking sig figs again, that 7.50 number, that is 3 sig figs. So when you have a 0 after the decimal point, it counts. So we want our answer here to have 3 sig figs. So it's the 7, the 0, and the 8. Those are what count for sig figs. 3 sig figs. All right, next part. It says if 0.550 moles of nitric acid react, how many grams of sodium nitrate will be produced? So again, our strategy, let's map this out. We have 0.55 moles of nitric acid. That was the HNO3. We need to convert that to moles of sodium nitrate. So we can jump right into using the mole-to-mole ratio because we're already in moles of nitric acid. So we would convert it to moles of NaNO3, the sodium nitrate. And then since it's asking for grams, then we'd have to convert to grams of sodium nitrate. So 2 conversions again. So 0.550 moles of nitric acid with 2 conversions. The first one, we need to cancel the moles of nitric acid, and we need to convert it to moles of NaNO3. For the numbers, we just look at our balanced chemical equation. So scrolling up a little bit, I see that for every 2 moles of nitric acid that reacted, 2 moles of sodium nitrate were produced. So we have a 2/2 mole ratio. So moles of nitric acid cancels. And then for the next one, we want to get to grams of NaNO3. We need to cancel moles of NaNO3. So we're going to use the molar mass of sodium nitrate again. And let's go and calculate that over here. And let me just erase what I have. So our formula is NaNO3 and sodium's 22.99, nitrogen is 14.01, and oxygen is 16. So we'll have 22.99 plus 14.01 plus the 16 times 3 for those 3 oxygens. I'm just going to calculate that really quick. So you should get about 85 grams per mole. I'll say 85.0 because I do get exactly 85.0 grams per mole. Okay, so that's what we're going to use. Go over here. So 85.0 grams per mole. So on your calculator, what you're going to do is 0.550 times 2 divided by 2. That's going to be the same thing. And then times the 85 grams per mole. And in terms of our units, we should have grams of NaNO3. And for the answer, my calculator told me 46.75. In terms of sig figs, the original value given to us had 3 sig figs. So we would actually want to round that to 46.8 grams of sodium nitrate. Okay, last one for this set. So it says if 500 milliliters of carbon dioxide gas is produced, how many moles of water was also produced? So this one's going to be just a little bit different because we're starting with the volume of a gas, and the conversion that we're allowed to use, it didn't say it here, but you can only use this conversion when it's at standard temperature and pressure. So we'll make that assumption here. So at STP, which is standard temperature and pressure, which by the way is 1.0 atmospheres and 0 degrees Celsius. But at STP, you can use the conversion that says 22.4 liters of a gas is the same as 1 mole of the gas. So that's a conversion that we can use. So 500, and the little dot, by the way, is saying that all of those zeros are actually significant. So if you just have 500, that's 1 sig fig. But if you say 500 with a little dot, that's saying all of those zeros are significant. So now it's 3 sig figs. So our answer, we're going to want 3 sig figs when we're done. Now we're first going to have to convert this milliliters into liters if we want to use this conversion. This fact that 1 mole of gas at standard temperature and pressure occupies 22.4 liters of volume. So we want to convert from milliliters to liters. And there are 1,000 milliliters in 1 liter because, again, the little m is for milli, which is 10 to the negative 3. So 1,000 milliliters is in 1 liter. And then that will cancel our milliliters. So now we could use the 22.4 liters of gas is 1 mole of gas. And I'm going to have to erase this to make room as we keep going. And this is for CO2. I didn't really write that in, but we have moles of CO2 in terms of our units now because liters has canceled. The last bit, we need to convert to moles of water. So we want to use our mole to mole ratio because if we want to go from moles of CO2 to moles of water, you're always using the mole to mole ratio from the balanced chemical equation. So scrolling back up to look at our equation one more time. getting very, very messy up here. Let me erase. But we have CO2 right here and water. So they're in a 1-to-1 ratio. For every 1 mole of CO2 that's produced, 1 mole of H2O is also produced. So again, it's kind of trivial, but it's really important to show that because you're really showing how your units are canceling. And you have to have the correct units in your answer if you want to get the problem correct. So in our calculator, we're going to do 500 divided by 1,000 and divided by 22.4, because that last bit is kind of trivial. Times 1 divided by 1, same thing. So I'm doing 500 divided by 1,000 and divided by 22.4 in my calculator, and I get 0.02231 mole of H2O. And we talked about earlier, this 500 with a dot at the end is a 3 sig fig number. This is also 3 sig figs. The 1,000 milliliters per liter does not count against your sig figs because that's an exact quantity. It's practically a definition. So our answer, we want 3 sig figs. So we will round that to 0.0223 moles of H2O.